When building modern software, the temptation to dive straight into the code is almost overwhelming. We start with a single blank document, and within months, we are managing thousands of interconnected files, services, databases, and deployment pipelines. In those early days, an architectural mistake remains practically invisible. The system still seems to work perfectly. Features ship on schedule, and the cracks in the foundation are hidden beneath a working user interface. But months later, a single harmless-looking structural decision begins to mutate. As millions of users arrive, that early choice suddenly triggers cascading performance bottlenecks, crippling downtime, or massive security vulnerabilities. At this stage, the cost of repair is catastrophic. You can't just tweak a few lines of code. The team is forced to migrate databases, redesign APIs, and tear down the entire foundation to rebuild it from scratch. We avoid this outcome through software architecture evaluation. This is the disciplined process of stopping to ask if a design is strong enough to survive reality before the first line of production code is even written. To answer that question, we weigh a design against 5 core pillars: reliability, maintainability, safety, security, and performance. Skip the search for the most technologically advanced design. Often, the ideal architecture is simply the most straightforward one that safely fits your constraints, your budget, your timeline, and your team's skills. Because of those constraints, engineers use the Architecture Trade-off Analysis Method, or ATAM. This framework exposes the reality that your quality goals are almost always in direct competition with one another. Look at this scale. Adding heavy caching drastically improves performance, but data consistency plummets. Users might temporarily see outdated information.
Similarly, breaking a system into microservices gives agility to deploy independently, but simultaneously spikes operational complexity as you manage dozens of moving parts. Evaluation is recognizing that there are no perfect answers in software engineering. It is the act of balancing these competing goals so your team can make conscious, calculated compromises. We test these compromises using qualitative evaluation. This relies on concrete scenarios, asking, what happens to the user experience if the payment service suddenly fails in the middle of a checkout? For more precision, we use quantitative evaluation. Here, engineers use prototypes and simulations to measure hard metrics, like predicting a 250 millisecond response time before the code even exists. We also have to set realistic targets. Google's site reliability engineering materials argue that demanding 100% reliability is an unrealistic constraint slowing innovation. Instead, teams use error budgets to balance uptime with the pace of change. This is why architectural context is absolute. A highly scalable, flexible microservice design is perfect for a global social media platform, but if you drop that same design into a banking system, the lack of central controls would be a disaster. Turn it around, and the result is the same. A startup social media app that adopts a rigid, heavily audited banking architecture will find its budget crushed and its development speed stalled. A design is only valid if its specific compromises perfectly match the intended real-world environment. In modern cloud environments, architecture evaluation is not a one-time event. Because these systems evolved every day, the evaluation must be a continuous process. We use observability as our evidence. Logs, traces, and latency percentiles show us exactly how the architecture is surviving production in real time. We apply this same pressure to security. Threat modeling identifies attack paths while the system is still on the drawing board. Security has to be designed into the foundation, rather than bolted onto the system after it's built. Ultimately, the difference between success and failure comes down to intention. Bad engineering teams make their architectural trade-offs accidentally, only discovering their fatal flaws when the system finally crashes. Good engineering teams make those same trade-offs consciously. They expose the risks and make calculated bets long before their software ever hits a server. Constructing a system is only half the battle. To endure, a design must be relentlessly evaluated, challenged, and refined against the pressures of reality.